Okay, here we go. All right. So welcome back to the second part of the second session, our afternoon session. So we have Vijay Balasubramaniam from University of Pennsylvania, who's going to tell us about black holes and complexity. Over to you, Vijay.
Great. Thanks very much. Can everybody hear me?
Yes.
Okay, great, wonderful. And you can see my screen and my cursor, right?
Yeah. That's...
I hope so. Okay. Great, wonderful. So I'd like to start by thanking Suresh and Gabrielle for organizing this workshop while we're all stuck with the pandemic. It's really, really nice to be able to get together with colleagues to discuss ideas. So today I was asked to give a review talk on black holes and complexity. And so I thought I would start by trying to talk about why, in some sense, we think about black holes as complex systems, and then move on from there to some of the most recent work. So, black holes are in some sense your quintessential complex system, perhaps the most complex system that we know about, and their dynamics is supposed to be complex too. And there's been a lot of effort in the recent past to try to think about what that means and how the complexity of the processes are related to other things that we know in physics. So I think so I decided to start by reminding you of why and how the physics of black holes leads to the idea that there's some underlying very complex system involved. So this goes back all the way, of course, to the work of Bardeen, Carter, Hawking, and Bekenstein in the 1970s already, where these authors observed that black holes satisfy several laws of mechanics that are an analogy with the laws of thermodynamics, namely that if you change the mass of a black hole through some classical or semi-classical process, that's equal to kappa, the surface gravity, times the change in area. That's an analogy with delta E equals T delta S. The area of the black hole horizon is non-decreasing in classical processes, and that's an analogy with the entropy being non-decreasing. And the surface gravity being constant at the horizon is an analogy to the temperature being constant in equilibrium, in a body in equilibrium. And this analogy between the dynamics, the classical dynamics of black holes and thermodynamics is even made stronger by the introduction of quantum mechanics, which led Hawking to show in 1975 that you can pair produce particles just outside the horizon of a black hole. One element of the pair falls in, the other goes out, and the net radiation looks thermal with the temperature required by this analogy between black hole dynamics and thermodynamics. So from this, you can conclude that at least semi-classically, black holes act like black bodies. And oddly, black holes are really, the Schwarzschild black holes are solutions to the vacuum equations of motion. So that's very odd because it's nothing there except at the singularity, if you like. But nevertheless, there is an analogy with thermodynamics. So the normal procedure in physics, at least for 100 years, more than 100 years, is that if you have a thermodynamic system, you seek to uncover the underlying statistical mechanics, the underlying statistical physics. In other words, we'd like to be able to say that a Schwarzschild black hole, namely empty curved space, is somehow the universal effective description of E to the S, where S is the entropy, E to the S, complex microstates. So one of the questions that's been important here, I think, for the last decades, is the question, what makes these microstates complex, right? What is it about the gravitational microstates that makes them so complicated? And why do simple infalling states, like elephants, black hole, elephants, encyclopedia dictionaries, whatever, why do they evolve into such complex microstates? So characterizing this complexity has been a very important problem for us in theoretical physics, not least to understand where these thermodynamic relations come from. So just to make it clear that this is not some sort of strange peculiarity about that particular black hole, I mean, similar conclusions obtained for gravitating universes in general. You can even take sort of literally empty flat space, and then study it from the perspective of a family of accelerating observers. Here they are in these green lines, and you will see horizons associated with these accelerating observers plus Unruh radiation. So many years ago, so you can show, therefore, that if you assume Einstein's equations of motion, then these accelerated observers see thermodynamics in the accelerated frame of reference. So in other words, these equations of motion of gravity become equivalent to equations of state in the description of these accelerating observers. So also many years ago, 25 years ago, actually, Ted Jacobson argued that if you do the reverse, just assume that accelerated observers see the thermodynamics of horizons, then you can derive from that assumption Einstein's equations of motion, which tells you that there is a sense in which the equations of motion and the equations of state are equivalent to each other. That somehow the equations of motion should be thought of as equations of state. This is a classic kind of thing that would happen in a complex system, where you write down an equation governing the system, and it's really an equation of state. It's an equation concerning the collective behavior of very, very complicated underlying degrees of freedom. And you can wonder, this is not specific to flat space, to zero cosmological constant either. You can consider positive cosmological constants like this, so here the vacuum solution is de Sitter space. You can consider the inertial observer de Sitter space who sees a cosmological horizon. That's the location L here. And then you'll find similar arguments occur there. So in general, we expect complex microstates in some sense of complex for gravitating universes. So you'd be led to ask, so what are these complex microstates? And that too, in string theory, in full-fledged string theory, there's been a lot of progress in the last few decades. So as we know, already in the late 1990s, Strominger and Waffe showed that large classes of black holes in string theory can be constructed as bound states of d-branes with strings and other kinds of things attached to them, and that you could try to count these things, how many different bound states there are, and you can explain the entropy of some black hole. So that's supposed to be the complex microstructure of the black hole. There's a space-time realization of this kind of thing. So Mathur especially, and Lunin, Bena, Warner, others, and Denef have talked about stuff like, if you try to ask what is the sort of metric realization, what is the gravitational realization of these bound states of d-branes, you find some sort of foamy structure with holes and bubbles and wormholes and what have you in sort of a dense gas at the Planck scale, if you like. And the argument that these authors and others have made is that if you have such a very, very complex microstate, if you like, in space-time even, then the universal response of typical probes of the typical such state will give you an effective black hole, whereas very atypical and precise measurements may sense the state. So the ongoing question, I think, for at least 2 decades now in the field has been, can we very explicitly show this in concrete models? Understand exactly what these complex microstates are, how they develop, why they're complicated, why simple probes can't tell them apart, and then piece apart how, if you like, the unitarity of black hole evolution is recovered by saying you send something in, something happens, it's very complicated, something else comes out, and you can read it out to find out what went in. So that's what you'd really like to do. Okay, so let's drill this down a little bit further. So a lot of the progress that's occurred in understanding the nature of these complex microstates has come from holography, right? So if you ask the question, what are the complex microstates and why are they hard to detect? One approach to doing this is, and it continues to be, you put the black hole in a box where it comes to the equilibrium with radiation. So the covariant way to do this, famously, is to make the cosmological constant negative. So this is the action. And with the negative cosmological constant, everybody in this audience knows that the vacuum solution is anti-de Sitter space. It looks like this. The geometry makes a potential barrier, so that stuff bounces back and forth in the potential barrier. That also means that if you write down a black hole solution, this is the ADS-Schwarzschild black hole solution, where the radiation coming off the black hole comes to equilibrium with the radiation. And in the end, you take that system and you try to understand. Now, as we know, string theory with asymptotically ADS boundary conditions is dual to some quantum field theory. So the efficient way to think about these microstates, why they're complex, and why they're hard to detect, and all of these kinds of questions that we raised, is to ask this question in the dual quantum field theory, where we just have so much more control over what we're trying to do. So the classic example of this is string theory in ADS5 cross S5, which is dual to the well-known SUN gauge theory with 16 supercharges on a cylinder. So let me remind you of elements of this correspondence, which we are going to use. So one element of this correspondence is the relationship between couplings. So there's the ADS scale L, the string coupling and the string length, and they are in various combinations equal to 2-dimensionless numbers. It's the Yang-Mills constant, G squared Yang-Mills, and N, the rank of the dual gauge group. The semi-classical limit for gravity, which we'll mostly work in, is n being much bigger than 1. And then there are other relationships. First of all, the space-time symmetries, isometries, are related to global symmetries of the Yang-Mills theory. And importantly for us, states in gravity with a mass m are related are created, if you like, or should be created according to the correspondence with operators with the conformal dimension m times the ADS scale L. So there's a relationship between the mass of the state in space-time and the conformal dimension of the operator that we're going to use to make the states. By the way, feel free to interrupt me with questions whenever you want. I'm happy to take questions throughout this talk. Great. So let's start by trying, using this correspondence, to get some feeling for why the microstates of the black hole are supposed to be so complex. So the way this talk is going to go is we're going to keep building on these. So first we'll try an elementary argument, then a less elementary argument, and by the end we'll be trying to come up with a dynamical argument why time evolution in the SUN gauge group is time evolution is complex in the sense of computational complexity theory. But I'm going to try to build things up slowly and relate the notion of complexity as people understand it in computer science to conventional notions that we're more familiar with in physics. So you'll see that as we go along. So great. So I'm going to try, therefore, in this correspondence, the ADS5 theory being related to SUN, to get some practical sense of what it means for the microstates of the black hole to be complex, so that we understand what the target is when we try to understand, more computationally what it means for these microstates to be complex. So let's consider black holes in ADS5. So that's this metric at the top here is the Schwarzschild black hole in ADS. And if you work out its mass, it's related to this R0 parameter here. And if you work things out, if you have a classical black hole, then the conformal dimension of an operator that constructs a state with this kind of mass goes like n squared, where n was the rank of the gauge group. Likewise, the entropy goes like n squared. And if it goes like n squared, that means you wind up having e to the n squared such microstates. So you have enormously many microstates of roughly this mass. Okay. So the question is, how do you construct such a microstate, right? So this is supposed to be a semi-quantitative argument, if you like, right? So how do you construct such a microstate? Well, a microstate is built in the Yang-Mills theory by constructing an operator out of some long gauge invariant polynomials, or sums of such polynomials in the fields of the theory. That's how you make operators in a Yang-Mills theory. I'm taking a perturbative point of view here as opposed to a non-perturbative point of view, and strictly speaking, we're at strong coupling, but permit me to do that anyway because it'll give us some insight. So we consider that in the Yang-Mills theory, what are the fields? There's the gauge field A mu, there's some fermion psi, and there's some scalars in the adjoint of the gauge group, X, Y, and Z. And what are you supposed to do to make an operator? Well, you multiply a long string of these, X, X, Y, X bar, Z, Z, X bar, whatever you want. And you need of order n squared letters, if you like, in this polynomial. And then you've got to sprinkle some traces and derivatives and other fields and so on. And that's how you make an operator. So now I'm going to try to make an argument to you that almost all operators that you choose to make of this length are basically going to be structurally similar, and it's going to be very hard to tell them apart from each other. And you'll see what the relationship of this to computational complexity theory in a little while. So let's make a claim. So suppose O is a microstate of the black hole. So you make it by applying one of these operators O to the vacuum, and let OP be any probe. So OP is going to be some operator with dimension of order 1. So that's going to be dual to something like a gravity field, the usual things that we use to probe black hole with. Now, what does it mean to probe the black hole? Well, in the language of ADS CFD, well, in the language of physics indeed, when you probe something, what you do is you compute the correlation function of your probe operator in the state, right? You hit the state with the operator and you see what happens, fine. So that's this correlation function. So I'm going to argue to you that at some level, such a correlation function for such a light operator, if you like, in such a very heavy state, will depend only on the conformal dimension and the global charges of the state you've made and of the probe, up to tiny e to the minus n squared, e to the minus entropy corrections. So you can go about doing this argument in 3 steps. The first observation is if you construct long strings like this, you can prove that almost all long strings are elements of something called a typical set. And the typical set consists of statistically random strings, right? So basically almost everything looks structurally random. So roughly speaking, if you look, what is the probability that a randomly chosen letter in this polynomial will be X, X being one of the adjoint fields, it'll be 1 over the alphabet size. So basically everything is used more or less evenly up to constraints. Then there's a theorem that says that if I ask the question, what is the probability that if you give me some particular operator, so some particular long polynomial with a letter distribution Q of X, what is the probability that it has that particular distribution Q of X? Well, it turns out to be e to the minus delta times the relative entropy between the distribution of Q of X and the uniform distribution that I mentioned over here. Okay, so so what this tells you is that as delta gets very big, so delta, remember the conformal dimension of these operators is n squared. These are very long polynomials. You can show that this means that the atypical fraction of operators is going to 0. Almost all operators that you can write down look statistically random. But this also then has the corollary that the statistics of randomness controls the operators. So for example, suppose I have a very long operator, this trace of many, many things making the state. So here's the trace, this operator applied to the vacuum making the state. Here's the operator dagger that makes the bra and the cat. And then you make a probe. And then if you start trying to figure out the combinatorics of how you put in a probe, here a trace XX over here, and try to compute the correlators, the combinatorics of how you contract the operators is also universal, and it's completely determined by the statistics of random polynomials. So this argues in this way that in some very, very practical sense, if you take standard kind of supergravity style probes, that is say light operators in the Yang-Mills theory, and probe very heavy operators, the answer is going to get controlled essentially by the statistics of random operators, right? And all of this, of course, immediately brings to mind many of the recent developments in things like the SYK model and JT gravity and stuff like that, except this is done in the full-fledged, or it's an attempt to think about this in the full-fledged Yang-Mills theory that's dual to the full-fledged string theory on the ADS5. So that you can see already in this kind of argument that there's a connection there. So you can push this and see that there is actually a very general argument about something like this. So here I try to do a specific kind of perturbative style argument in the Yang-Mills theory, but I'm going to try to argue now that on totally general grounds, you can conclude that, if you think about a black hole and you try to probe its microstates, it ought to be possible in a unitary way to read off what the microstate is from infinity, except that it's going to be very hard and going to take you a very long time. So let's see, what's the very general argument? So let's just suppose that black hole entropy arises from some space, some discrete space of underlying microstates. That's all we're going to assume, that this, so the entropy means something in the sense of statistical physics. There's some discrete space of microstates. So well, in quantum mechanics, the spectrum of the Hamiltonian is generically non-degenerate up to symmetries. So this must mean that up to symmetries, rotations, what have you, each of these discrete black hole microstates must have a unique mass up to symmetries. But in gravity, mass is a notion that's measured at infinity, right? It's a Gauss law thing that measures mass. So this immediately tells you that a precise mass measurement done by an asymptotic observer will allow you to identify the black hole microstate. So then in what sense are these microstates complex, and what sense is it hard to recover information by probing a black hole? Well, so the question arises in how precise this measurement at infinity needs to be. So how precise does it have to be? Well, let's see. So suppose you have an entropy SFE. This tells you that there are n states within the measurement precision delta E. Well, so let's suppose delta E, the measurement precision is, I don't know, some multiple of the Planck mass. Let's take that. So this tells you that the level spacing between the black hole microstates must go as e to the minus entropy of the black hole. What does it take to measure energies with such precision? Well, we also know from quantum mechanics that delta T, delta E is bigger than you get the H bar. That means the amount of time you need to make a measurement with the precision required to resolve the black hole microstates, which you can do, goes like e to the plus entropy. That's just 1 over the gap here, right? So it's e to the plus entropy. But the entropy goes like area over 4 g Newton H bar. So this means that at fixed A, G, and H bar, if you send H bar to 0 in the semi-classical limit, the amount of time required goes to infinity. So what this says is that all the information about the state is actually present at infinity, can be read out, but the semi-classical observer, the simple observer if you like, simply can't access it in the limit H bar goes to 0. Okay, so again, this is very reminiscent of many of the recent developments in the field. So, for example, there's lots of discussion lately about things like the island formula, which is supposed to help recover the unitary part of the page code. What the island formula is really saying is that if you include Euclidean wormholes, then gravity, the gravitational theory, knows something about the finite dimension of the underlying Hilbert space and thus monogamy of information and things of this kind. So again and again, we get this idea that somehow the gravity gives you a coarse-grained description of the underlying space of microstates, but of complex microstates, but nevertheless, it knows something about the number of these microstates. That's the information that survives into the semi-classical limit. So, okay.
So can I ask a question?
Yes, yes.
Samir, where
Sorry.
in this? Oops.
Let me try to get back to the actual this one.
Yeah. In this argument, is it crucial that you're talking about a black hole? I didn't see where the information that there's a horizon comes in. This should apply to any gravitational system. Right?
Yes. The only thing that comes in about it being hard to measure is the entropy of the system.
Yeah.
And
So if you have a star, it's the same thing.
Except that the entropy of a star doesn't increase at such a tremendous rate.
Yeah. So okay, good. Mm-hmm.
Yeah, absolutely. So the argument here is that there is nothing really, what I'm really pushing on again and again and again, is the only thing that's strange about black holes is the immense density of states. Mm-hmm. And the immense density of states, to get that, you require quantum gravity. This is not, the density of states is non-perturbative in the Newton constant and H bar. So you need the quantum gravity to give you that. And then much of what else follows, including many of the recent developments in the island formula, this, that, and the other, are really following from the statement that you have so many states with this gap, with this tiny, tiny gap. And a lot of the mysteries are coming out because of that. That's what I'm trying to go after. Mm-hmm. And then we're going to try to keep breaking this down again and again, and doing this again and again, and trying to see what makes the thing complex. How do you see how the complexity increases with time and things of this kind? Did that answer your question?
Oops. Yes, thank you.
Okay, great. So let's go to the next thing. Okay, great. So let's push on this again. So you might say, well, you've made two arguments. One is a sort of a qualitative argument, the last one that I made. And before that, you took the n equals 4 Yang-Mills and kind of constructed operators and everything. So we can be even more precise. Here's an explicit example where you consider the m equals 0 BTZ black hole. So as you recall, the BTZ black holes are black holes in 3 dimensions, my favorite kind of gravity because there's no local graviton. Here is the m equals 0 black hole. And we know that this system can be embedded in string theory on ADS3 cross S3 cross C4. And this is dual to the 4-4 supersymmetric sigma model on T4 to the n mod Sn. So that's the free limit of the theory, really strictly speaking. At finite coupling, there's some deformation of this theory that's necessary. We also know there's a correspondence in ADS-CFT. I'm just trying to give you another example to show you it's not a special case that I was discussing earlier. The m equals 0 BTZ is related to the L equals L, well, some particular sector where the Virasoro generators are 0 and the R charges are also 0. Fine. So there's some particular sector of that kind. So there's no need for us to go into the details of the calculation here. I'm just trying to show you that these things exist. You can write down operators corresponding to every single microstate of the BTZ m equals 0. They are known to be products of certain twist operators in this two-dimensional conformal field theory. You can write down all such operators, and then you can demonstrate that almost all such operators lie close to some typical operator that's constructed in the following way. It's some product of bosonic and fermionic twists, and the bosonic twists are extracted from this distribution, and the fermionic twists are extracted from this distribution. This is straight statistical physics. As in, you just say that you have a certain total twist you have, you need to distribute them among some number of bosons and some number of fermions. You can give this to a first-year graduate student, and they will compute this, and this is what the typical operator looks like. And you can show that almost all operators look structurally very similar to this with little fluctuations around this. So then you can also ask, given this construction, in the conformal field theory, you construct a state by applying this operator to the vacuum, and you can ask, how does the probe react to the typical state? Notice that this state looks very complicated in the sense of being statistically random. These states are statistically random in the sense that there's no rule telling you how many of the bosonic and fermionic twists to keep, how to order them. None of that is specified to you. It's statistically random, right? So then if you ask the question, how does a probe react to this typical state? You can calculate this. So if you construct a non-twist probe, at least in the orbifold limit, you can simply do the calculation of the 2-point function of this probe in this state. And what do you get? So I won't do the calculation for you because I really want to get the latter part of my talk. But the calculation, you do whatever you have to do the calculation. You find that you construct a particular microstate, and then you do this calculation. And for a long period of time, you get an answer which is smooth. And the smooth answer looks exactly like the answer for BTZ. It's exponentially close to the answer that you would get by doing correlation functions in the gravitating BTZ solution, by computing propagators in the BTZ solution. And then after that, you find quasi-random fluctuations, right? You get these bumpy things, these pseudo-random fluctuations that depend upon the detailed form of the state. You pick a different state, you get a different detailed fluctuation. In other words, those fluctuations tell you what the state is. It just takes a very long time to get to them. And then you have to be very precise in your measurements, even when you get to them, in order to be able to read out the state. That's exactly the kind of picture we're trying to tell you earlier. So let me draw the analogy with the recent developments with the SYK model. There was an interesting paper some years ago by Stanford et al. Talking about the SYK model. And in the SYK model, they demonstrated that if you compute, in their case, a spectral form factor, but you can compute correlation functions too, there's a dip and then a ramp and a plateau. So if you take this model, right, the full-fledged D1, D5 string and compute its correlation functions, you will find that there's this initial dip. Then if you sort of average things out here a little bit, if you time average a little bit, you'll find that there's a ramp and then there's a plateau, precisely the phenomenon we were talking about, right, in the SYK model. So the same physics of that kind. Some details are different. The details that are different are because we're talking about the sort of orbifold limit. This system is actually secretly integrable. So this ramp persists for less time and the plateau is a little bit higher than it is in the SYK model, which is fully chaotic random model, and which this should be. The D1, D5 system should be when you turn on the coupling, but it's hard to calculate all the details when you turn on the coupling. But you can see this precisely the same effect. You can see an echo of those effects as you go to the weakly couple limit. So again, from this we see the lesson that the microstates of this BTZ M equals 0 black hole are some very complicated random polynomials, if you like, in the elementary fields of the system. Somehow universally there's an effective classical geometry describing the early time physics. The late time physics has quasi-random fluctuations which kind of average out to a ramp and plateau. So, well, if you were willing to make sufficiently precise measurements, you could read out the complex microstate, but semi-classical observers are going to have, or simple observables are going to have a hard time doing that. So once again, we see the same message done very, very concretely. So what's more is we've learned over the last decade now, I would say, that there's also a very interesting dynamical aspect to this problem. It isn't just that the states are complex. So far I was talking about make the state and it looks complex when you probe it. But we've also found out that black hole formation manifests various kinds of complex dynamics. So there's information scrambling. There's chaotic time evolution and thermalization, and the result is effective thermalization of pure state. So you basically start with some simple state and it does whatever it has to do to itself and becomes effectively indistinguishable, perhaps because of chaotic evolution and information scrambling from what looks like a thermalized state. So here's an example of computing the 2-point function in three-dimensional, in ADS3 gravity, ADS4 gravity, and ADS5 gravity. You use holographic techniques to compute the 2-point function. This is really the log of the 2-point function, and what's being plotted on the y-axis, the difference between the log. Oh, I should have written this down properly. This is the log of the 2-point function minus the thermal 2-point function. This should be log of this minus the thermal answer. And as you see, as time passes, it rises from whatever it is initially. This is during a quantum quench. And so you start off the quench, you calculate, you compute the 2-point function. It starts off wherever it is for different initial separations x. And then after a while, it looks thermalized, though you know perfectly well that in the quantum field theory, dual to ADS space, this is a perfectly unitary process. All you did is to drop in some quanta, and there's nothing non-unitary about that. So you see here, once again, this idea that somehow simple states become complex states. And from this, you could derive a conjecture, right? So Susskind has conjectured that black holes have complexity somehow in the dual quantum system have complexity that increases linearly in time for a time exponentially in the end and exponential in the entropy. The way in which Lenny came up with this conjecture is he was considering the physics of ADS black holes and realized that the volume inside the horizon keeps increasing for a very long time. And he was looking for a quantity that could conceivably increase for a very long time in the dual field theory, and suggested that perhaps that could be the complexity. So in other words, this is the source of this conjecture that somehow the holographic dual of complexity in the field theory is the volume of regions in the bulk spacetime. So I'm not going to have much to say about that conjecture specifically. What I'm instead going to do is I'm going to slightly generalize Lenny's statement and say, well, the thing that's characteristic and interesting about the dynamics of black holes is because of the evidence like this, and because of the evidence from the concerning chaos in these systems, we believe that the process of black hole formation generates complexity by being maximally chaotic. So we could slightly generalize Lenny's conjecture to say that maximally chaotic processes, all maximally chaotic processes, such as black hole formation, have linearly increasing complexity for time exponential in the entropy. So this is basically taking a conjecture coming out of holography and generalizing it a little bit to talk about maximally chaotic processes. So the challenge with trying to understand this conjecture, which is what we're going to spend the remainder of the time discussing, is the question of what complexity means, because we could have many different meanings for complexity, and that's what I want to turn to now. So I've used the word complex in many sort of intuitive but qualitative ways. You know, it looks random, it looks complicated, there are many pieces to it, it sort of interacts in many different ways. You know, everything is there are many things happening at the same time. So we've used that qualitatively. So I'd now like to be a little bit more quantitative about what we might want to mean by complexity and try to relate it to other things that we're already familiar with in physics. So first of all, I want to remember in computer science, how do people think about complexity, since we've used the term so many times here. So the idea of complexity in computer science goes all the way back actually to the work of Kolmogorov, who suggested that the complexity of an object is the length of the shortest program required to reproduce it. So in this sense, pi, or the square root of 3, are relatively simple, even though there's lots of digits in them, because there's a short program to produce the digits of pi, even if it's complicated looking. However, a truly random sequence in this language is complicated because there's no way to compress it into a short program. You just have to write down the digits because there's no order in it. Remember how we were discussing the black hole microstates operators that we discussed look like random polynomials because almost all of the entropy lives in the random polynomial. So that's the sort of moral connection, I think, that's underlying many of these developments. There's a related notion due to Jorma Rissanen, who coincidentally won the Kolmogorov medal. Anyway, so this is the notion of stochastic complexity. And he was thinking in the language of communications theory, where you're sending a message from one station to another station. And in his kind of reasoning using information theory, the complexity of a message is the size of the smallest code for compressing it as you transmit it. So building upon these kinds of notions, in computer science in general, the complexity of a class of problems of size n is understood to be f of n, which is the size of the smallest programs calculating the answers. So there's a scaling relationship you try to derive between the size of the problem and the size of the program. So how can we visualize the size of the program? If you were doing circuit complexity, which is the language that's most attuned to think, computation of qubits, you imagine you have a bunch of bits here and you have a bunch of gates and you sort of stack up the gates and you can ask how deep the circuit has to be. You can ask how wide the circuit has to be. You can ask how many gates have to be put into the circuit. Anyway, pick your poison, pick a definition of size of circuit, and that's supposed to compute the answer. So these are all computer science notions of one kind or the other, and barring this connection between sort of randomness and complexity, you might wonder, what is the relationship with everything I've been talking about with black holes so far? Well, okay, so in black holes, really underlying, there's some kind of quantum mechanics, right? We're talking about a quantum gravity of some kind. So we're really interested here in thinking about quantum mechanics as a computation to sort of come to grips with this notion there. So in quantum mechanics, how do things work? There's some initial state, psi naught. There's some time evolution, e to the minus IHT, which leads to a final state. And let's ask what it would mean for this time evolution to look simple or complex. So suppose you had a situation where you start with some initial Gaussian wave function, it spreads out a bit and becomes a bit bumpy. Well, I would say that this looks kind of simple, right? There are some small local changes to this wave function, but nothing else happens. It looks pretty simple. I imagine that I could make the second state from the first state, if I wanted to do that right now, by taking a quantum computer and applying a few local operations here and there, and it would make this from this. Now imagine the time evolution starts from the simple Gaussian state and makes this very, very complicated jaggedy wave function with lots of non-local entanglement over here and things like this. Now this seems complex because it would appear that if you told me right now, I want you to convert this lower state into this upper state, you need large global changes and substantial non-local correlations and entanglements. So your machine would need to sort of produce correlated actions in many distant qubits and things like this. And that's what you need to do. And therefore, this seems kind of complicated. Okay. So
a question.
Yeah.
These pictures that you drew seem to depend on the basis that you choose.
Yes.
Now,
so
yeah. So, I could just choose a very complicated basis where something on the left looks very complicated, right?
You are completely right. And I do think that complexity is a notion that does depend to some degree on the basis. So for example, in computer science, the complexity of a system depends on the gate set. So they depend on asking questions about natural gate sets. And a lot of work goes into computer science in showing that if I define my favorite gate set and you define your favorite gate set, that in fact, the results from my gate set are polynomially equivalent to your gate set. That is to say, up to some polynomial, it gives the same answer. So I do think in physics, we have the same situation. I don't think we can get away from this. We either have to define a natural gate set or ask the question that we want to answer in a different way, right? So conjectures like complexity equals volume, the immediate obvious question was, what do you mean? And define for me your gate set first, right? So here we're going to try, so I'm going to try, you'll see, we'll try to argue that if you tell me what the physical qubits are, then the natural gate set involves local operations, operations on a certain number of qubits. That if you actually already have a structure that you call space-time, that physical locality in space is something that is natural to include as a definition of what simple operator means. But this is an important discussion, and I'm not going to solve it entirely for us. But we should have. Would it be possible to pursue this discussion further at the end of the talk?
Great, thanks.
Yeah, but you're right. Yeah, it's clearly a basis dependent statement in that sense, right? It depends on the gate set. But given this gate set, where I've taken spatial locality as somehow paramount, we could ask, how can you construct a measure of this complexity and then relate it to other properties of interest in physical systems? I'm sort of ultimately interested in going back to those black hole problems that we cared about in the beginning. So one approach to this would be to consider the complexity of states. So you have this state, which has two little bumps in it, and this state, which is complex and has lots of bumps and non-local correlations. The reason why this may not be the best thing to do, to look at the complexity of states, is we're really interested in asking, what is the complexity of states that arise in some natural way from physical time evolution, right? It's what does physical time evolution do that's really characteristic of the system, right? We don't just build arbitrary states, we allow the Hamiltonian to build a state. So we really are interested in asking the question, what is the complexity in some sense of time evolution? So if I think about U of t, this time evolution operator, as a computation, I'd like to know as a function of time, how complex is the operation performed by this U on the state? Okay, so I'm going to take a cue from the computer scientist and say, well, what do I do? Well, what is time evolution? So here I'm going to imagine some Hilbert space with many copies of the complex plane, and then time evolution is simply some SU 2 to the n over 2. I'm dropping the overall phase, right? So it's n over 2 because we're going to take the SYK model as an example later. Okay, so what is time evolution? Well, I start at the identity, and the operator U of t pursues a particular trajectory on the unitary group manifold. There it is, right? And in some way, how complicated this is. Well, if I take the cue from something like computer science, here's an operation here, all these tick marks are sort of discrete steps I need, and you sort of want to count up how many steps do you need to go from one side to the other side. That's sort of the complexity, you'd think. Well, so let's think first about the nature of this. So this seems like an easy problem, work out what these trajectories are like. It isn't, because although SU2 is simply the sphere, and so this is easy to do, SUN is some really complicated fiber bundle with all kinds of interesting local geometry in it. So this problem is actually in general not solved, understanding trajectories on the unitary group. That's the core of the question of how complex is time evolution, understood as some trajectories e to the minus IHD. But if you were going to take the idea from computer science, you would say, how complicated is this trajectory? Well, if you discretize time, then in some sense, the number of steps you need to take along the curve, in other words, the length of the curve, the appropriate metric, is some measure of its complexity. A little bit more accurately, what you really want to say is the complexity of this time evolution, this curve on the unitary group manifold, should be the length of the shortest path from the identity to the endpoint, to U of t. In other words, the geodesic along this, because that's actually, in some sense, if you like, the shortest. If the goal is to say the complexity of this operator, U of t here, is the length of the shortest program, you want to find out the shortest trajectory on the unitary group that would get you from the identity to this one, to the operator U of t. The challenge is what metric should be used, right? Because the idea is that some directions in the unitary group are complex and some directions on the unitary group are simple. So you've got to define what we mean by complex and simple. So there are results from about 15 years ago by Nielsen and Nielsen-Dowling, which basically says that the geodesic length on the unitary manifold in a certain metric, which we'll discuss in a bit, is polynomially equivalent to quantum circuit complexity. So in other words, if what you wanted to do was to generate this U of t by using some finite number, some gate set, some natural gate set acting on finite numbers of bits, and you want to add it up, you can define corresponding to your gate set some metric on the unitary group and then compute geodesics in it, and those geodesics will give you back up to some polynomial the actual circuit complexity, how many gates you need to do to get from here to here. Now, in physics, we don't really care about gates. It's not a bunch. We're not in discrete time. We're in continuous time. So actually, the geodesic length on the unitary group manifold in whatever the appropriate metric is seems like the right thing in the first place. So what I'm going to do now is I'm going to spend a little time discussing what metric should be used, and then I'll tell you the results using that metric, and then we'll have a little bit of time at the end to discuss how those results are derived. So that's the plan. So here, consider the unitary group. In the unitary group, infinitesimal operators along the tangent are defined as linear combinations of the generators of SU2, SUN over 2. So going back to Samir's question, for our purposes today, we're going to imagine that the system consists of some discrete number of qubits. So we're not quite doing quantum field theory yet. We can discuss what to do in quantum field theory at the end of the talk. So we're going to take some discrete number of qubits, lots of them, and we'll imagine that a simple operation is k local. That is to say, it acts on less than k elements at the same time. So that's a simple gate. And k, you can pick k as you wish. And the complex operation is not k local. It acts on more than k bits at the same time. Now, there's no condition of locality. In some ongoing work that I've been doing with a student, Kathy Lee, we have in fact found that if you actually have a system with physical locality like a spin chain, it's important in this definition of what you mean by simple to include not just k locality in terms of number of bits, but also how close they are, as in things that are contiguous are simpler than things that are far away. That's an important consideration to include to get interpretable results. So let's come back to that later. If you have physical locality, you should probably include that in a definition of what local or simple means. So but the short answer, Samir, to your earlier question is we're going to use locality as a notion of simplicity. Okay. So the metric that we're instructed to use by Nielsen should be small in the k local directions and should be large, in fact, exponentially large in the other directions, in the complex directions, where S is the log of the dimension of the Hilbert space. Okay. So this kind of picture tries to capture the idea that an operation is complex if you have a correlated action on many, many elements. If you act in few elements, it's simple. If you act in many elements, it's complicated. Okay, so our goal then is there's some trajectory that the real-time evolution operator satisfies from the identity to U of t. There's some geodesic in this metric that goes from the initial point to the final point. We compute the length of that geodesic in the metric. And following computer science people, we understand this to be a notion of complexity, right? So that's a definition of what we want to mean by complexity. There are several questions here. Can you compute this? That's the first thing. If you can't calculate or prove things about it, then it's kind of useless. That's the first thing. And the second thing is, can you show that it reproduces the properties we wanted, like sort of this linear growth of complexity for, let's say, for chaotic systems or something. And third, can you relate this seemingly obscure notion of geodesic lengths of the unitary group to anything else that we know in physics that might connect to the microstates of black holes, their structure, etc. So now I'm going to tell you the results that we obtained. And then in the 15 minutes, I think, that will remain after that, or 10 minutes that remain after that, I will tell you about a schematic of how we obtained that results. So we will show, or we showed in some work that we did, several things. So first of all, let's suppose that the Hamiltonian is a linear combination of the simple generators like this. So T alpha are supposed to be the simple generators. Then our claim, the first claim, is that there is always a linear geodesic between the identity and U of T that sort of basically falls along the trajectory made by the Hamiltonian. And that it's always there in a metric where the Hamiltonian is made of simple generators. And along that linear geodesic, the complexity increases linearly in time. So that's what we wanted, right, for these maximally chaotic systems. But this thing is always there. No guarantee yet that this linear growth persists for an exponentially long time. Secondly, this linear growth indeed persists for a time exponential in the entropy of the system, in the log of the dimension of the Hilbert space, provided the following condition is satisfied. So let me read out the condition and let's talk about it a bit. So the condition says, so we call this condition the eigenstate complexity hypothesis. And I'm using a notation where alpha indexes k local or easy generators and alpha dot indexes hard generators. So in the numerator here of this expression, you have a sum over easy generators of m T alpha n squared, where T alpha are the easy generators, M and N are energy eigenstates. So we're deriving here a relationship between this notion of geodesics on the unitary group to things like eigenstates and energies and stuff like that of a physical system. So that's in the numerator you have this, and in the denominator it's normalized by sum over both the easy and the hard generators of these overlaps squared. Okay, I'll talk a little bit more about this quantity in a little bit. So this quantity Rmn if this quantity Rmn is goes like e to the minus twice the entropy of the system times a polynomial in the entropy of the system times some numbers of order 1, then it's a fact that this linear growth and complexity, persists for an exponentially long time. The third thing, which I will not have time to show in this talk, but anyway, I don't have time to derive all the results in this talk anyway. The third thing that we showed is that the SYK model for large N, namely a chaotic system that's actually solvable, satisfies this criterion. And thus, its complexity growth is linear for an exponentially long time, and matching the holographic prediction coming from black hole physics. Okay, so those are our three results. So that's all fits with what we're hoping this definition of complexity will do. It gives us a quantitative notion that we can relate to other stuff in physics, and that realizes this idea from holography that the complexity of the, if you like, the microstates generated by such a system will grow for a long time. So let's just talk
Sorry, just to clarify. So in this second point, M and N are
yeah.
If Rmn equals that for all M and N, is that the point? Yeah.
Yeah. So this is for all M and N. Now you could ask, well, is it sufficient to have exponentially M and N? Is it sufficient to have polynomially many states M and N satisfy this criterion? And the answer is I don't know that. So what I can tell you is the criterion, as we stated, is sufficient to achieve this result. We don't know if a weaker criterion would suffice. My own secret hope is that by asking questions about what fraction of states satisfy this criterion, I mean, because M and N, remember, are both states, right? Eigenstates of the system. by asking what fraction of the eigenstates satisfy this criterion, I have some hope in the back of my head that we can sort of classify degrees of chaos. Remember that in real chaotic systems, it's not like, so suppose you take a system where there's a parameter that you can tune, like there are spin chains where you can start at one end, it's free, you turn on the coupling, it's integrable, and then there's some critical point beyond which people say it's very, very chaotic. Actually, if you look at the system, what actually happens as you turn on these couplings, there are regions in parameter space where such systems become chaotic. So there's these little islands of chaos. And then when you cross some critical point, it's chaotic everywhere. So in some sense, there's amounts of chaos. There are systems that are chaotic to some degree, or chaotic in some regions of phase space, but not other regions of phase space, and things like this, sort of mixed systems of this kind, integrable in other regions and stuff. And then they eventually become chaotic. So we don't have an order parameter to distinguish these different kinds of things. And I have in the back of my head that this object can be such an order parameter for reasons that you will see, perhaps can be such an order parameter, and thereby by saying, polynomially many MNN or exponentially many MNN or whatever else satisfy this criterion, you'd be able to distinguish such systems. At least that's the hope. Just let me say one more word here, which is that let's just think about what this means. So what this says is that if n is an energy eigenstate and T alpha is a simple operation, then this condition says that a simple operation will not transform one energy eigenstate into another energy eigenstate. That's exactly the intuition that we wanted to express. Here, this criterion just came out of the analysis of the problem, of the geodesic problem. It did not come out from us imposing this. But what it actually says is that the linear growth and complexity of this definition of complexity persists for an exponentially long time, provided it is difficult to transform one energy eigenstate into another energy eigenstate. You cannot do that very easily. And so you can't do that using k-local operations. So that's exactly the intuition that we wanted to express. And it's very nice. It came out of the analysis rather than being put into the analysis. I'm happy to take another question or two, but then I would like to give you some sense about how these results are derived. Okay, let me move on. So our goal, so the analysis that produces these results is fairly technically involved. So what I'm going to do is I'm going to give you kind of a roadmap through how the analysis is done. So we're really interested in geodesics on the unitary group, on some SU group. And so our working model in the back of our head is going to be the SYK with n Majoranas. So as you know, that's, the Hamiltonian is a product of up to, let's say, if it's Q local, there are Q fermions, Q Majoranas, multiplied by some couplings. The couplings are chosen to be random numbers chosen from a Gaussian with some variance. So we need a basis now for the unitary group. And so one way of getting a basis for the generators in the unitary group is to take the gamma matrices. And you can take, in the SYK model, the gamma A can be associated with psi A. So what we do is, so it's actually more convenient to sort of reorganize this a bit. And so we reorganize this in the following way. So you can rewrite the basis in the following way. You take products of gamma matrices, ordered products of gamma matrices, what these are, and I'm going to give that the name Ti. So anyway, that's another basis for SU for this unitary group. And in this basis where it's more convenient for us to do calculations, it turns out that, okay, so if you take this basis, there are two things we can say about it. One is some of these basis elements could be considered simple because they're acting locally on no more than Q on a certain number of fermions, K fermions. And some of these basis elements you could think of as complex because they're acting on more than K fermions. In any case, you can work out that their commutator has some form, and you can write down the metric we wanted in terms of the Cartan killing form. So if you write down the Cartan killing form in terms of the structure constants, that's this quantity here, and that's often what we take as the metric on the group. But instead, what I'm going to do is I'm going to multiply the Cartan killing form by certain cost factors. So here are the cost factors. And the cost factors are going to be 1 for the k local or simple directions, and are going to be 1 plus mu, where mu is exponential in the entropy with other directions. So I'm going to take a deformed metric, which is large in the non-k local directions, and which is small or order 1 in the k local directions. And the way we're going to compute the metric at any point, a point on the group, is that if I have two tangents at u, that's x and y, I'll pull back x and y to the origin, and then I'll apply this metric at the origin, and that's going to be my definition of the metric I'm going to use in the group. Okay, this reflects the idea of Nielsen that the complex direction should be exponentially weighted. Now it's just a it's just a calculation at this point, right? You need to solve the geodesic equation SU2 to the n over 2, and happily Euler and Arnold. There's something called the Euler-Arnold equation, which basically which is this thing, and this is the standard geodesic equation written in a convenient way with the standard Levi-Civita connection on the group. So what do we want to do? We want to solve for geodesics of this in this metric. Given to us by the essentially a modified version of the Cartan killing form. And the boundary conditions are U of 0 is 1, U of 1 is the time evolution operator, and the complexity is the geodesic length. So I write down all the geodesics, I find the shortest one, and then I take, I compute the length. So completely standard at this point. So what do we get? So let's not, in view of the time, I'm not going to do the example of SU2. Instead, I'm just going to go on to the answer. So you write down the Euler answer. We're going to skip the details of the calculation, and instead we're going to say you write down the non-local. You write down these equations. They have some form in terms of the local and non-local generators, and let's come to the solution of these equations. And you find out that one solution that always exists in this to these somewhat complicated equations is that you can flow in the easy directions at constant speed. So if you take V alpha, the initial velocity, is along an easy direction, and as the geodesic parameter S progresses, well, the unitary operator you're talking about is e to the VI alpha, T alpha being a tangent in the simple directions, and times S. So if H, the Hamiltonian, is K local, so it's J alpha, T alpha, you can work out that, well, the correct direction to go in is along the Hamiltonian. And if this is the shortest geodesic, then the complexity grows, quadratically, square root of a sum of the coefficients squared in the Hamiltonian times the time, as you would match with holographic expectations. So once again, just to emphasize that this is a completely practical calculation. This is simply solving the geodesic equation, this equation here on the SUN group manifold. So you get this. So really our question is, what obstructions are there to this? When and how can the linear geodesic stop being minimizing? And there are basically two ways in which this can happen. So one way this can happen is because of geodesic loops. So what happens is there's a global effect. You're going around this way, and somehow it turns out at some point that there's a path that went that way, and it came back around and turns out to be shorter. So we're not going to address this. Showing the absence of global obstructions of this kind is actually, in general, it's computationally hard. What we're instead going to do is think about another kind of obstruction, which does happen. So this is important to eliminate, which is something called a conjugate point. So you imagine here's the original trajectory. And now I deform the original direction a little bit. So I sort of basically go sideways. And then you sort of bounce off the, if you like, the edge. There are these complex directions that are producing a potential well, kind of glance off that potential well, and you come around and meet the original trajectory again. And then you can deform this kink a little bit to get a different path. So if such a conjugate point happens, then it's possible that you have a shorter path between here and here, and that would mean that the linear growth in the complexity stops when the first conjugate point hits. So what we're actually going to check is, what does it take for conjugate points of this kind to be absent? Okay. So to do that, you take the original geodesic and you perturb it a bit, and you need to solve again. So there's an equation for that. So you start with the original linear geodesic, you perturb it, and then you need to solve the geodesic equation for the perturbation. This thing is called, this first order perturbation of the Euler-Arnold equation goes by the name the Jacobi equation. Again, we don't need to work through the details, some complicated mess, and actually really complicated mess, right? So in this talk, there's not time enough to talk about this formalism. But you can go look at our paper. Roughly speaking, the way in which we solve things is we say to ourselves, well, we define a super operator that maps an inertial perturbation to the final point. And it turns out that this super operator that maps the initial perturbation, this operator perturbation in the trajectory on the group onto the final point, this thing has a this deformed trajectory meets the original trajectory again if there is a zero mode for the super operator. And so what you can do is, so it turns out that the conjugate points are zero modes of this super operator. So again, we did not discuss the details of that formalism. So instead, I'm going to tell you what the solution looks like. So here's the super operator that maps the initial perturbation over to whatever the final thing is. So you can work out that the eigenstates of this super operator are the projectors Mn, where M and N are energy eigenstates. And so if you plug that into this formalism, it'll turn out that you get a zero mode when okay, so you work this out, and then you can work out what the eigenstates are. So if you have the projector M and N, Mn, for which are two energy eigenstates, it has a coefficient phi Mn. So a zero mode occurs when this phi Mn is zero. And I haven't told you how to derive what this phi Mn is, but it takes the following form. It's e to the I delta Mn minus 1, delta Mnt minus 1 over delta Mnt, where delta Mn is the gap in energy between the two energies in the projector. See, one of the very nice things here is we've reduced a geometric problem in computational complexity into things about energies and eigenstates and stuff like that, which we can handle more easily in physics. In any case, if you want this quantity, this eigenvalue to be zero, you need to take the time Tmn to be 2 pi over delta Mn. So it's basically whatever it's 2 pi over the earliest conjugate point. The earliest zero happens when delta Mn is as big as possible. So in other words, it's the largest gap in the theory you should put in there. So in the SYK model, the largest gap is of order n. And so you see that this isn't the free theory, by the way. Sorry, this isn't the situation of all directions are considered easy. So we don't consider only k local directions easy. So if you take that, so you take the metric on the space to be exactly the Cartan killing form, you find that the first conjugate point in the SYK model will happen at a time of order 2 pi over n. So the large n limit happens almost immediately. So that tells you that if you consider in the SYK model that all operations are easy to perform, then no matter what the time of the complexity in the sense of computational complexity does not increase linearly for a very long time. In fact, after time of order n, whatever operation this SYK Hamilton is performing, you can perform it faster by doing some very complicated thing with many bits at the same time, with many fermions at the same time. So instead, let's now suppose that k local directions are easy and non-k local directions are not easy. Turns out in this case, if you assume this eigenstate complexity hypothesis condition, this condition that I told you that one energy eigenstate is hard to transport into another energy eigenstate using a simple operator, namely such overlaps as suppressed exponentially in the entropy, then you can again work out that the eigenstates of the operator mapping the identity over to some other later point on the time evolution trajectory, like that super operator, has eigenvalues of the following form, where you have e to the I delta Mn t over 1 plus mu, where mu was the cost factor that weighted the complex direction, that suppressed the complex directions. Okay, so then that's what you get. And if you work out what that means, it turns out that the answer for the first conjugate point is 2 pi over the maximum gap times 1 plus e to the epsilon s, where s is the entropy. So we've left out some details of the analysis, basically because I'm out of time. But what you see is that the first conjugate point is pushed away to exponential time because of this factor, which tells you that many of the operations that you would have liked to perform to get the time evolution operator out of simpler building blocks are forbidden because they're very complicated. They cost you a lot to do. So as a result, if you're forced to stick with simple operators mostly to do your operations, it'll take you exponentially long before the first conjugate point appears, and therefore truncating the linear growth in complexity. Okay, so there's some consequences then for ideas in for conjectures in computational complexity theory. But I think I'm out of time, so I'm not going to mention this unless someone else asks me, and then I can tell you about that, and I'll tell you the summary. So we started out by saying that black hole microstates are complex, simple operations cannot distinguish them, and we gave some explicit constructions in string theory demonstrating one and two. So that's the prehistory of thinking about complex systems, thinking about black holes as complex systems. We then discussed, very briefly that another insight over the last decade has been gravitational dynamics can transform simple initial states into complex microstates through scrambling and thermalization, things like this. So then really the second half of the talk was focusing on, well, what does this even mean, right? We've talked about complex in some qualitative way. It's very complicated operators, very long operators, they look random, etc. So what does it exactly mean? So using the algorithm, so then we try to develop an algorithmic notion of the complexity of time evolution, borrowing ideas from computer science, and then showed that this thing that we call the eigenstate complexity hypothesis, which is a condition on the eigenstates and eigenvalues of a system, this ECH criterion gives an explicit criterion of the structure of states that does lead to complex time evolution in the way that we expect from holography. I'll stop there, and I can always go back and answer more detailed questions if you have any.
Thanks a lot, Jay. So, questions, comments?
So I have a question. It's not very sharp, but since nobody else is asking, so I guess it's this point 4 that I'm a little confused about. So if you think of some shell of dust forming a black hole, then there's a point where the horizon is formed, and is the idea that somehow that's when the system becomes more complex or something like this, or yeah, so that's one kind of vague question I have, and the other one was how do you map what you just said in the second part to anything relating black holes? I mean, you said you expect that there's a linear in tau, but why do I a priori know that linearity is the same as the one you're talking about?
So let's answer both, one after the other. Both are good questions. So the first question is, if you have a shell of matter following it, when does this become complex? I don't think the question can be answered that's as easily as that. I think the complexity increases in some steady way. Maybe there's some sudden jump here and there. As you know, the horizon doesn't just form at some instant. The horizon is, in the black hole is clearly some global construct, and it's starting from zero. There is indeed a moment where the shell is supposed to be crossing the horizon, right?
Yeah, sorry, can I just interrupt?
But that may be neither here nor there in terms of the complexity of the system.
Yeah, I mean, in the beginning of the talk, you were emphasizing that how the horizon is not a global property, that even local observers see horizons and so on, right?
Well, not exactly. I was emphasizing that accelerated observers see horizons, but the horizon that they see is, in some sense, a global construct because it's it separates the region that they cannot see. So that's a sort of global thing. But local observers see that because of the particular reference frame they're in, because globally the asymptote of light. That's all.
Okay.
Can we? Can I move to the second question? So the second question you asked is, what is the relationship? I tried to allude to this, but what is the relationship in the things being said in the second part with the first part? So okay, so there's a linear growth in this definition of complexity. How do you know that it's the same linear growth that you're seeing? In particular, that the original idea, one idea was that it had something to do with the linear growth of the volume or something like that on the black hole side. So I don't think we know that it's the same linear growth. So my own attitude to this is that first of all, if you want to claim that complexity is related to linear growth of, volume, action, whatever you want on the gravity side, you need to first give me I know how to calculate actions and volumes, right? But I have no idea how to characterize complexity. So I would like a formula that I can compute, right? I can't guarantee that the way we are computing complexity here is the thing that is holographically dual to some geometric construct. For that requires a proof, and I certainly have not given you that, right? But this is an object that can compute, and we've made some progress.
What about? I mean, can you?
Wait! I'm not finished. So there's a further comment I'd make. There's a further comment I'd make, which is that ultimately I don't actually really care if this particular notion of complexity necessarily relates to the black holes as we describe them. So in the end, I view the black hole, or geometric construct in the black holes, like the area or the volume or the action. As far as I'm concerned, really the thing that's weird about black holes is their extremely high density of states, and then the dynamics that reaches you into them. From simple initial states, it becomes one of these things. So that's some kind of very highly chaotic system, and there are different degrees of chaos. So I think the interesting thing to take away from all of this development is the question, what are meaningful and useful ways of characterizing the complexity of states and time evolution in field theories and quantum theories? And is there a way of using that to clarify the physics of such systems? And then I think that if you apply that clarification to the particular systems that have this insane density of states that we see in quantum gravity, then these kinds of properties will arise. The SYK model happens to be one such. It's very simple and all that stuff, it's a 2D gravity, this kind of thing. But still, it happens to be a case where there's a high density of states and there's some relationship with the physics of JT gravity. And so it's satisfying that in that case, these things line up. But there's a long way to go to make those connections precise.
I see, thanks. Yeah.
You had a further question, which
No, I was just wondering if I think you answered it. Even if you don't have a map of the two observables on the boundary and the bulk, experimentally you calculated something. Does it match something? Can we just try to sort of explore what it matches in the bulk or something like that?
We could, but the argument I was trying to make is that actually the thing that I find most interesting about the thing we calculated was not that it matched something in the bulk. Mm-hmm. The thing that I found most interesting was the statement that there was a concrete notion of complexity. We could prove how long this complexity rose without making if someone had told me without any reference to black holes at all, right? No reference to black holes. I have a system of n qubits, and I consider acting on k bits or less simple and more than k bits complex. Please compute for me, how long it takes for this conjugate point of view, how long the linear growth and complexity lies. That's an interesting question. So truth be told, my initial graduate degree was in computer science. So before I became a physicist, so I find this kind of question extremely interesting of characterizing precisely how complicated a computation is. I find that very interesting in its own right. I also think that because there is this connection which we try to enumerate between this complexity growth and this kind of criterion. Notice that this criterion looks a little bit like the ETH criterion, right? I can say thermalization hypothesis criterion. It's not the same. And it's not clear if one is a subset of the other or they're related. What the interlocking is also not completely clear because if you check, these exponents are not the same. There's some slight differences actually. Okay, but it is similar. So what I find exciting is that there is a direct relationship between this kind of quantity, which is, what is this? This is energies and, structure of eigenstates and amount of overlap with some operator stuck with. These are all stuff I can handle in physics. I understand it, right? And then there's this other concept, which, a priori is not defined for us by and large. What does it mean, the complexity of time evolution? That's not something that I particularly studied. In my graduate quantum class or something, right? It's not a thing we do, but it's interesting that there is a relationship, and between these kinds of notions, and that a certain characteristic of the space of eigenstates and eigenvalues of the Hamiltonian leads to an extended complexity growth. By the way, this does have consequences for computer science problems. So, for example, that's what I was trying to write up here. There's a conjecture about something called P space and BQP/poly. So P space is the space of problems that can be solved in a classical computer with space polynomial in the problem size. So this is and as much time as it wants. This is a huge class of problems. And BQP/poly is what's called bounded error polynomial quantum. So quantum means it's a quantum computer. Polynomial means you have a polynomial, circuit. Bounded error means, if it's quantum mechanics, you're going to make mistakes. So you got to tell me, sometimes because of the probabilistic calculation. So you got to tell me how you're going to bound the error. So you bound the error. And actually this class allows polynomial sized hints. Namely, someone can give you a hint and the hint is polynomial size. That sounds wacky, I know, but this is something called an oracle computation that the computer scientists like. So there's a statement that due to Aronson and Susskind that P space is not contained in PQB poly if and only if the complexity of time evolution operators after certain times exponential in n. So so basically our construction, if for a theory that satisfies ECH, our criterion, this conjecture is true. So there's actual consequences in terms of these kind of computer science things. There's also something called Hamiltonian speedups. So what we're saying also has another consequence, right? So a Hamiltonian speedup is you're trying to do a quantum evolution. That's your computation. Let's suppose you're trying to simulate a real physical quantum system, right? A real Hamiltonian. You could ask, can I do it faster on my computer? Right? Wouldn't it be nice if you had to do some quantum chemistry problem or something, you have to do some time evolution, but you could do it faster because you have a clever algorithm. That would be nice. So that's called Hamiltonian speedups. I think basically our results show that if you insist on, our results basically show that that's not possible if your operations are simple. So it's only possible if your machine can do extremely complicated things. So you'll have to, presumably you can invest a lot of energy or something like that to do very complicated things. But if you restrict yourself to simple operations, you cannot speed up the Hamiltonian. Right? So that's a consequence. There are these consequences of that kind. Now the relationship to black holes itself, what would I dream of here, right? So what I would dream of here is that is to be able to establish in detail, right, in some sort of very concrete way, how it is that the time evolution that you actually do in quantum gravity produces these very complicated states, how complicated they are and how much more complicated they grow over time. I'd also like to be able to know in general, use this kind of criteria to separate different kinds of, if you like, classes of chaos. Somehow, different kinds of degrees of chaos ought to be related to different amounts of complexity of time evolution. I mean, there should be that if it's more chaotic, somehow the complexity grows faster. If it's less chaotic, somehow it grows slower, right? Something like that should be true, regardless of whether we're talking about black holes or not. Right? And I do think that the kind of criteria we're trying to come up with here could help separate such theories. Okay.
Any further questions? All right, let's thank Vijay again. Thanks a lot, and thanks a lot to all the speakers. So that ends our session for today. We'll reconvene at 9 tomorrow, Lisbon time. In the meantime, we have a YouTube channel to which all these talks have been just uploaded. Feel free to check them up. We will send you a link saying at the end of each day, so that you can check out the talks again. Okay, thanks a lot.